Intro to Machine Learning. Today I'm going to go through exactly what machine learning even is, the different types of models, the learning workflow, some popular models, how they work, and then some examples of each of these models, from linear to logistic regression, decision trees, random forests, all with visualizations, and even going so far as support vector machines. Then we'll finish off with feature engineering, hyperparameter tuning, over and under fitting, and techniques to address this. Now this is going to be a very thorough video and real deep dive into machine learning, so if you had one video to watch, this is the one. Now I'm giving this to you all for completely free. This is a paid notebook and I will link it down below if you wanted it for reference, but everything here is 100% free. So let's begin. And if you have already had this intro before, or you get some of the basics and you want to skip right to how the models work, just jump ahead in the video. First off, so machine learning is a branch of artificial intelligence. It focuses on developing algorithms, so models, that allow computers like the one you're watching this on to learn from data and make predictions or decisions, like should you do something or not, or is something a cat or a dog, or how much will a house cost in 1 year. Now, you don't explicitly program them. Here's an example: predicting a flower based on its attributes. We train the algorithm with a data set of historical features of flowers, and the algorithm learns these relationships, allowing it to make predictions on new unseen flowers. So how does this work? At its core, machine learning works by splitting the data. The majority of it goes to a training set, and some of it, usually about 20%, to testing the model, just to see how well it performed after it was trained, and you know how well you did. Now, through this process, the model learns to generalize from your training data to new unseen data so it can make its predictions. Now, here are the main types. There's supervised. This means you have labeled data, so you have lots of data, as we'll see later. We'll go through exclusively supervised models. Now you have this data, so you have flowers, the type of flowers, roses, daffodils, and for each of those all their features, their petal length and so forth. There's actually a data set for this in Python, which we'll take a look at. And then it learns from these labels how to predict and map inputs to outputs. Unsupervised is where it does this without the guidance. So you can use this to cluster similar points together. Finally, we have reinforcement learning. Now, some of these you can mix and match together, but reinforcement learning is where it learns to interact with the environment based on rewards or penalties. But today, we'll focus primarily on supervised, and you'll learn that very in depth. If you want to take a look here is the exact workflow. You start by defining your problem, seeing what data you have, crucially pre-processing it. We haven't gone into that in depth here, but I have previous videos discussing pandas for Python. Make sure you are dealing with null values and duplicates. Equally, you may want to scale your features. What you could do is create a new feature entirely through feature engineering, or just transforming the ones you already have. Then you select your model, train it, evaluate, and deploy. This is the fun part, where you get to introduce new data and watch it predict. So here are some popular models. Linear regression is very simple. It's the first one I learned, and it predicts a continuous outcome such as height, weight, or age. It does so by finding the best fit of data points, minimizing the errors between the observed and predicted, so you can see how much something will cost by following that line. Logistic is typically used for binary classification tasks, saying something is one thing or another, such as it's a cat, a dog, spam email, or not. Decision trees, this is where you follow it down through the structure of nodes and leaves, and through this, you're able to come to a single answer. When you have multiple decision trees, that's known as a random forest. You have a bunch of trees together, each trained at a random bit of the data, and at the end it averages your result to come up with one answer. We also have k-nearest neighbours, which we don't actually focus on in this workbook, but we do have support vector machines, which are really interesting. Essentially, they cut a line through your data, known as a hyperplane. It can do this both in 2-dimensional and 3-dimensional space, to try and divide up the margins between each classes of your data. Now, we're going to be using Scikit-learn for this, also known as Scikit-learn. It's a very popular and open source machine learning library for Python. It's great for data pre-processing, model evaluation, and integrating your models and various different libraries. They all sort of follow the same theme, as you'll see. For example, They all start by loading a dataset, pre-processing, splitting it as we discussed earlier, that training and test set, choosing a model, training and evaluating. So let's begin. Now, first of all, it's important to note, like I said, I'm using the Jupyter Notebook with the Anaconda distribution of Python. You can use any environment. People typically use Jupyter Notebook for data science because you're able to execute individual cells and also see visualizations inline. So you can see them right in your workspace. Once you have Python installed and you're all set up with your Jupyter Notebook, make sure you have the following libraries installed. You can do this by going to your command line or terminal, your CMD, and write pip install scikit-learn, numpy, matplotlib, and seaborn. Now, these two are visualization libraries. NumPy is for numerical computations, and Scikit-learn is just the sklearn library for machine learning. But now, into the bit you've been waiting for. Linear regression. This is where we'll start because it's where I started. Now you'll note they all sort of follow a very similar theme. You start by, from sklearn, importing what you need. Now in this particular case, I've directly imported a dataset from sklearn's own datasets. You could use one from your own by using pandas, and we get to that later. But let's just say we import one right from them rather than using our own. Then, as you'll always need, from sklearn.model selection, we import the train test split. This is used to divide our data and is a crucial step in the process. In fact, it's the same with all of these supervised models. And speaking of models, we're going to use linear regression. So from sklearn.linear-model, we import linear regression. And we want to evaluate how well it performed. So I've chosen to use the metric here, mean squared error. Although there are a number of different metrics you can use, and all of which are stored inside sklearn. So I'm going to load the data set which we imported. I'm going to store it under the variable data. The way I'll get this is a bit different to pandas. I'll just write data is equal to fetch California housing. We can actually take a look at this too. And don't worry about this, I've just converted it into a pandas data frame just so we can take a quick look at it. Now in the X values, we have stuff like the house age, the average rooms, like we discussed earlier, the average occupants, and then if we look at the Y values, what we're trying to predict, it will be the price. So we'll see here, here's the target variable. So once we've imported it, the next crucial stage, and again, we always do this, is we split it here. So we say X, and typically we use X in capital, that's just a convention, whereas Y will be lowercase. Data.data will be all of the X features. Everything we just looked at with the latitude, longitude, number of rooms, average occupants, and parts like that. We're going to use all those features to predict the Y, which is the outcome. See how X influences Y, how we can use X to predict Y, which is the price. Now here's where it may look a bit complex, but don't worry, we're going to break it down for you. Here we do X train, X test, Y train, Y test. That is equal to the train test split that we imported earlier. And for that, we're going to use X and Y. The test size is 0.2 or 20%. What that means, 20% is going to be used for testing and evaluating how well it did, whereas the majority, 80%, is going to be used to actually train the data. Now, we have the 42 random state. This is quite arbitrary. You don't even need it. And in fact, if you do include it, it could be any number you want. The reason we have it there is so that when you run this, it makes sure the split is exactly the same for you, so you'll get exactly the same results. Next, we're going to initialize and train our linear regression model. So the model we picked was linear regression. Remember, we imported that earlier. I don't want to write that out every time. I'm going to save it as model. And then I'm going to fit it to my training data. I want to train the model. So X train and Y train. And from this, we can actually then make a prediction. So our Y prediction will be predicting based off the X test to see how well it performed, to make a prediction on the test data. Then again, we're going to evaluate the model. Mean squared error, we'll store that under MSE for short, is going to be y-test and y-predict. Finally, we're just going to visualize this with matplotlib using a regression plot. So all I'm doing here is I'm setting the size of the plot, making sure I have the imports. It's using Seaborn specifically, but matplotlib to make some amendments to add a title and some labels. X is y-test and Y is y-predict. It's going to be a scatter with this color, and we're going to have it plotted like that. So if we run that and ignore this second part, here we can see the predicted values versus the actual. And you can see the line quite well fits through all of the data, which is good. It seems to be quite a good fit. Looking at that mean squared error, it is 0.5. Now 0.5 is relatively low, which is considered good. The lower the better. So we're quite happy with that. We'll keep it for now. But say we wanted to run a prediction of this, and you can see that's what this is here. Now, and as I said, the deployment, this is the fun part. We're going to give it some new unseen data. So for each of those variables, I gave it a new value, each of those features in the X. Then we pass it through and print what it would give. And this would be the price. Fantastic. Next is logistic, and trust me, this will make more sense as we go through it. We're going to look at that iris data set, which isn't to do with eyes, it's flowers. Don't worry, that got me too. And that's what I mentioned at the beginning. So again, very simply, we're just going to import all the similar sort of things here, not the same, because we're going to load the iris data set this time. And then we're going to do the train test split, logistic regression as our model, and then a means to evaluate it. Here, the accuracy score rather than mean squared error. So we'll load in our data just the same as before. We'll set the actual data as its features to the independent capital X variable and Y as the target outcome or dependent variable. Easy, see how we're breezing through this now. Then we'll split the data. We start with both the X's, X train X test, and then Y train Y test, because we train it and then we test it. That's one way to remember it. So train test split, X capitalized Y. We're going to set the test size to 0.2, 20%, and random state to 42. Now just bear in mind that X train and Y train, as you may have guessed, will be used for training the model, and X test and Y test will be used for testing and evaluating the model. Cool. So we're going to initialize the model as logistic regression, storing it here. And with logistic regression, we're going to fit that to the training data, the X and Y. Now we're done. You've actually built your model again, this time logistic. And here you can now make predictions. So your Y prediction will be model, well, logistic regression dot predict based on the X test data. So as I've put my comment here, we're going to use the trained model to make a prediction on the test data. It's all coming together now. And again, we'll calculate the accuracy score, how well it's done, just by saying accuracy is equal to the Y test and Y predict, the dependent variable outcome. And again, I had a look at how many features there were. And for this, I gave it some random new value. And based upon that, it made a prediction. Now, interestingly, the accuracy is 1 and predicted class is 0, 2. So what does that actually mean? Now, there's a few ways to check. You could just go to Google if you didn't quite know and say, what is accuracy in machine learning? Or let's get a bit techie here and use some AI and head over to ChatGPT. Now, you can see here, it actually said the model accurately, because the accuracy, got 100% of them right. This isn't actually necessarily a good thing. You can see it predicts it as 0, 2. Well, this means it predicts the first sample to being class 0 and the second to being class 2. But let's prompt this a bit further because I don't 100% agree with that. So you can see here, it's a good sign, but it also means, is it going to generalize well to unseen data? And there's some other variables to take into context as well. But at the moment, do you know what? We're happy with it. We're going to leave it. Coming down quickly to decision trees. These are really interesting, and the way they work very quickly is just like that. You see they break up saying petal length less than 2.45. True and false, well if it's false, then it's likely to be this. Else if it's true, well, is it less than 4.75? If it is, then here, and so forth, and it breaks it down till it becomes to a specific answer, so it can use that to make a prediction. So, let's do that here. Again, all of these are very similar, and you're starting to see that now. We're importing all the same, in fact, even the same data set here, the iris one. The train test split, I'm sure you're getting old of this now, just hearing it over and over, but that is good. The decision tree classifier, that's what we import for decision trees. Here, the accuracy score, and then a plot for the tree. Equally, I imported matplotlib here just so we could do some further visualizations. Now, we're going to load in the data set. And it's actually in this part of the video, you're going to see a real world example. If we scroll down a bit further, here's an actual example using a pandas data frame of actual data. So not just using the model's data. Once we split the data up into X and Y, the independent and dependent variables, and then we started with the X and gone to the Y with the X train X test, Y train Y test is equal to the train test split, X and Y, train test size or test size 0.2, 20% for the testing data, 80 for the training, and random state, again, we'll stick with 42 just so you get the exact same results. Then again, we are going to initialize the model. You see I even specified here specifically within those brackets for it to be 42. The model is the decision tree. We're going to fit it to that training data for both X and Y. Then we'll visualize it. We're going to plot it here, making sure the feature names are on and the class name so we can actually see what it's plotting out. You don't need to do this, and I found when you have a really big data set with a lot of classes and features, you really can't see anyway. It's quite hard to zoom in and see what they're all saying. So this is just an extra visual step for us to learn. Once we've plotted it, then we're going to make a prediction using the train model to make a prediction on the test data. And we're going to do this through yPredict is equal to predicting on the X test. Finally, we're going to evaluate the model. So we're going to use accuracy score for this one, and we're just going to print it here. Now, to give it new data, we've given it this. And you can see based on that, it will predict exactly what type of class it is, 02. Now again, you're thinking this is to do with flowers. Why is it saying 02? That's not a type of flower. Let me explain. Well, this is the class in the dataset, class 0 and 2, and that's what it fits to. So you can reference that to the flowers in your dataset just to see which one those actually are. Now there's a reason it does it like that. It is a lot easier for computers and machine learning models to work with numbers, but we can map it back to those values. We would do it like this. Now, the way this works, if we hit run, you'll see that it maps it right back rather than 0 and 2 to the actual name of the flower species. Fantastic. This will make a little bit more sense if we use some more realistic data. Here, all the same steps, but instead I'll import pandas as PD and we'll read in a data frame. This is shopping trends, and we're going to use some more easy to understand variables. Age, review rating, and previous purchases. Just the amount of time someone has shopped there before, what they rated an item, and their age. And we're going to use this to classify the location. So following the same train test split with the 42 and 20%, fitting the decision tree to model and training it on the training data X and Y, we'll get a prediction, visualize it, and then when we print the accuracy score and give it new data, it'll give us an actual value. Now you'll see this won't run if you don't have the actual CSV. Luckily I do, so let me import that into my folder and then it should work. There, and you'll see what I meant by having a much bigger plot like this. Now, We could see here it's given us a better answer, Missouri, but the accuracy is 0. That is not good. And why is that? Well, it's probably showing us that we have some quite irrelevant features, or it's really overfitting to the model. And this would mean we're taking that with a real pinch of salt, a handful, but we'll learn to address that later. Now, random forests are just when you have a bunch of decision trees. And here, rather than looking at this example, I'm actually just going to jump straight into my real world example using the same data set. So let's hit run on that. Here, very similar, we're going to use the same features, and you're going to see it again, because it's not a great data set. We're going to get 0, and again, it's still going to predict Missouri, as it did above. So at least it's consistent, if nothing else. Now, using a more accurate data set, which you probably should use, such as the California housing, we can use all these features to predict the target, and this is what we're going to get. Which isn't too far off what we predicted earlier with the linear regression using the same California housing data set. So not too bad at all. 4.151 for linear regression, and random forests 4.265. A little bit off, there's some variation there. But how it works again, it will typically give you a better performance compared to a single decision tree. That's because it aggregates the predictions of multiple decision trees and all looking at random subsets of the data. Each tree might only consider certain features as well at any given split, which further diversifies it. Each tree makes its prediction independently, and then it's either averaged or you look at the mode just to see what the single answer will be. And finally, support vector machines, this really cool one, which I'm quite a fan of myself. This is how it works. You import the libraries. Here we're also going to import NP for numerical computations, as well as the iris dataset for the flowers, train test split, the support vector machine, and the accuracy score. Now, again, same data set. We're going to use that same xtrain, xtest, ytrain, ytest to the train test split, capital X, lowercase y. Don't worry, this is the final model. Test size 20%, random state 42, initialize the model as model. Now you'll note I specified here the kernel is linear, and we're going to fit it to the X and the Y train data. We'll make a prediction. Our Y prediction will be using the X test data. So use the train model to make a prediction on the test data. And we'll evaluate it here again with the accuracy score. We'll go ahead to give it new data. Here's an example of what you could put in, and we'll make a prediction for that new data, printing it here. A lot better. Accuracy is 1. Predicted class is 0, 2. And again, we could map that back to something more meaningful. Here's a real world example using our not so great data set, which is why it's actually not included in this package when you buy it. You just sub this out for something else. Now, we discussed feature engineering earlier. It involves creating new features, so new columns or values or variables based on existing features just to improve the model's performance. Techniques could be imputation. So for that, say you're missing a value, you could use the mean, median mode of that column to substitute that missing value. One-hot encoding converts a categorical variable into a numerical format. That's very useful. As you could see earlier, we did sort of the opposite. We have feature scaling as well, just making sure everything has a similar range, so we're all on the same page. Feature selection, well, that's just what it says, picking the most important features that actually have some relationship. And if you have a look up here, if I change some of these features and didn't use, for example, these, which may have no correlation, you'll find there will be something. Now, hyperparameter tuning is when you find the optimal set of hyperparameters for a model, just to improve its performance. Now, this is getting a little bit more complex, so we won't get into that today, but it's something important to bear in mind. Finally, because I briefly mentioned this earlier, overfitting is when the model learns to capture all the noise in your training data, meaning it doesn't actually generalize to new unseen data. Underfitting, on the other hand, is when the model is so simplistic it doesn't capture any of the underlying patterns at all, let alone generalize to new data. There's a few ways to address this. You can reduce the model's complexity. You can use ensemble methods like random forest, like we've discussed, or gradient boosting, which we're not going to focus on today, just to reduce that. Now, to address underfitting, well, increase the model's complexity. Use some feature engineering to make more features. So there's a lot that you can do. Now, all the best. Good luck.